Um, it's early, so there's a few of us, but that's okay. I'm not an early person normally either. My name is Migüel Jetté, and yeah, I'm here to discuss and show you a little bit how we built what I think is the world's best speech recognition system. And so I call it meaningful because we want to build a system that works for everybody and that have the least bias possible. And it's AI plus human hybrid because, well, you'll understand later in my slides how we use a sort of Uber for transcription marketplace to build this amazing system. But before I go in, I just wanted to introduce a little bit my why, and why I'm passionate about voice technologies. I grew up in Quebec, Montreal, to a French-speaking family. And, when you want to learn something, especially on the internet, everything is in English. Everything is like sort of inaccessible if you don't speak English. And so I got really interested in languages early on to learn and so on. And so to illustrate that, I like this slide, because everybody knows GPT and Whisper, and this is the distribution of the training data in it, which is just to illustrate how, lump-sided or biased the internet is. Everything is in English, basically. And so I really like voice technologies and trying to make content more accessible for people, who don't necessarily speak English or want to learn English. And so that really what, started my interest in speech early on. All right. And so just a quick, introduction on speech recognition history. Basically here you see, I tried to, visualize a lot of things in one slide, but basically you see Rev's history in the slides compared to speech recognition and AI, if you will. And then at the bottom is sort of my career and what I've been doing. And so I've been doing speech recognition since 2006. Back when, I guess, machine learning was not necessarily popular or almost a thing. But yeah, it's been a crazy journey. And basically, you see the graph, I tried to sort of show the level of hype around AI, so at the beginning, when I was born in the 80s, things were like, so working okay with hybrid systems and GMM systems. And then there was this uptick in deep learning around 2006, right around when I started at Nuances. And then things got a little bit better. And there were these things, this system called Caldi, which was built at CMU, at JHU, sorry. And things started to pick up a little bit and get better, and that's when you started to have things like Siri, and these systems that were starting to be pretty cool, But really things changed in 2017, around 2017, which is around when our first ASR was deployed. Since then, things really just picked up, real fast. And now the systems today are just quite unbelievable, actually, if you compare to what we had 17 years ago. So it's quite an exciting time to be in AI. And Rev is just in the middle of all this, enjoying the ride. So yeah, quick little introduction here of a long history. And then I figured I would start with my conclusion so that if you start to doze off or check your emails, you can already have the takeaways with you. So for me, throughout my career in speech, what I found was important is, well, first of all, find, why you're working on this. Why you got to be passionate about what you're working on. And so for me, it's accessibility at scale, which I think is only possible with AI. Just making everything more accessible, being able to learn a new language and read content and There's so much videos out there right now that's coming out, and it's nice to have captions and things transcribed. My second takeaway is when you're building ML, there's a thing called align by design, which is basically make sure you're building AI and ML systems that align with what you want it to do, right? And so for us at Rev, we built this human and AI system that just by design is making sure we build something that adds value to our lives, and not just a pie-in-the-sky AI model. And the third thing that I'm going to talk about is bias in, bias out. So in computer science, there's like this thing called garbage in, garbage out. But in ML, if you're not careful what you feed your model, you're going to get garbage out. And so I often tell my team, pay attention to the details, or like the devil's in the detail. And I'll talk a little bit about data preparation and so on later in my talk. So that's, my why. But really, want to tell you a little bit about the what we've built at Rev. And so earlier, I was introduced as Rev being the Uber for transcription, let's say. So early on in our history, we started as a transcription company that created work-at-home jobs, for people who would want to work from home. They can, sit at their computer and transcribe. And really what that did is that it gave us an opportunity to have this sort of virtuous cycle where now, today, when you upload an audio at Rev, it runs through an ASR engine, and at the top here, it goes into our marketplace with 75,000 people working, and then they correct all the mistakes. We send the transcript to our customers, but then we can feed back all the corrections into the system so that the Revers and the customers are training the AI so that it gets better over time, And I think if there's one thing you can remember, try to build systems like this with human feedback back into your system. I think it's the only way to get, really accurate AI systems. So yeah, I say maybe this is the most important slide in my talk. All right, this is the coolest slide in my talk, but. Basically, the system has enabled us to accumulate a lot of data over time. I don't know how many are familiar with speech recognition systems, but coming from a world where I train models with 10,000 hours of audio, 20,000 hours of audio, now Whisper is trained with 400,000 hours of audio, of English audio. At Rev, over the 13 years, we've accumulated over 6 million hours of transcription. And so that gives us a huge data advantage and really kind of like an amazing, fun place to work at for ML scientists to sort of dig into this data and try to build a cool system. Today we use a fraction of this data. We're working really hard to try to use more of that data. And then there's all the customer and Rever corrections that we can, fold back in the model. And I tried to gear my talk to ML practitioners. So the next slide is more around just to show the progression of the work we've done. And I specifically removed customers from that slide because I just wanted to show how long it takes sometimes to build a really good system. So, and also, that's kind of a neat slide. When I was alone at Rev for the first year, the accuracy was maybe 38%, the word error rate. And then I hired a few of my old friends, and we started working on it and made progress. But really, it's, as my CEO likes to say, it's a game of inches. So when you make progress, like every week, every month, every quarter, and you just keep focus, you can improve your system over time. And by the end of this year, I think we'll be below 7. So hopefully it keeps just adding up. The other thing that the other advantage data gives you is that it for us creates a model that has less bias. This was a third-party study that was done with one of our partners where they compared us to, well, back then Amazon and Google, but they compared us to a bunch of other competitors, and they found that Rev system, at the time we were going from Rev 1.0 to 2.0, was behaving better for a lot of segments of the population. This company particularly cared about bias a lot, so they did a really thorough study. And so it just goes to show that if you have a system with humans in the loop that kind of review thing, and you have enough data, you can really create something that works for everybody. So that's the what, and that's kind of what we built at Rev. Now I kind of want to just give you a little preview of how. And so a lot of people that joined the team, they are very excited at training models, and I tried on day one to tell them, most of your time will be spent on data preparation and testing. So it's not as cool as training like a 70 billion parameter model. A lot of your time is just spent, looking at data, trying to make sure you're training on the right stuff. So first, I'll just quickly, show one advantage of having this human in the loop system is that we can do live monitoring. So that's part of our testing. We do a lot of different testing, and we release a lot of benchmarks for speech recognition. You can ask me after the talk if you're interested. But the live monitoring is really the most powerful thing because every file that comes through Rev gets corrected, and so we can track in real time the accuracy of our model for different customers, for different releases of our model, and so on. And so we can really track, A/B testing experiments and so on. And we can learn which words we're getting wrong, and we can add them back to the model and so on. And really, I think this is probably the most powerful thing that we have at Rev, because we can just try a lot of different models and make sure that every improvement we make is positive and so on. And yeah, the behavior of the model is a bit weird on the right there, but over time it is improving. So. Yeah, so that's a powerful sort of byproduct of having AI and human work together in your system. Okay, so I talked about testing it a little bit. I'll just really quickly introduce, the notion of data preparation in speech. Yeah, it's a bit different in speech than in other ML, work, because you're working with not only with text but with audio. And so part of the job is to align the audio and the text together so that you can train the system as accurately as possible. And so just to illustrate that here, I have this earning calls from an airline company. And basically you're trying to go from this big transcript to these little segments, because neural network training cannot see a huge sequence of words. You have to keep it relatively small. And so there's a lot of work that goes into creating these little segment files and so on. And honestly, a huge portion of the last 8 years of my life. So one of the things is you have to align the audio with the text. And so you can imagine that, visually looks pretty simple, but actually pretty complicated to align 3-hour transcript to a 3-hour audio file, right? And so we do this through something called force alignment, but we do it while biasing the force alignment with the transcript. And as part of this, what we decided to do, not everybody does, but we decided, this was a decision we made, was to transform the text into a spoken format. And so, for example, here you have he had at least $60 on him. It's not obvious how the person spoke that $60. It could be 60, it could be $60, it could be $60. And as part of our forced alignment, we try to to transform it at the same time. And so I call it alignment problem in our data prep. And that is fairly, compute intensive and takes a long time, so you don't want to do it too often. So we've built a system at Rev that does that, on a daily basis with all the audio coming in. And then another part of the data prep is segmentation. And so really, I was saying earlier, you can only show about 20 seconds to the model when you're training it. And so part of, the alignment is finding where to cut, the sentence so that you can train your model appropriately. And you can imagine word timing is very, very important, because if you cut, if in the audio it said he had at least, but I cut it at the wrong place, then I'm teaching my model to learn the wrong thing, right? And so you can have problems with insertions and deletions later on. And it gets really messy when you have like a million hours of these little segments, right? Nearly impossible to find, why your model is hallucinating or creating deletions. And so that's another fun part of data preparation. But, I think most people like ASR training, so I'll talk a little bit about it too. So I was saying earlier, you have, when you're training the model, you have both an audio and text, right? So how do you represent that audio? So maybe most of you know already, but we do something called feature extraction. So the audio on top, it goes through a Mel-scale filter bank process where you go from the audio up there to a spectrogram at the bottom, and basically, you create vectors. I think it's 25 milliseconds every 10 seconds, every 10 milliseconds. So you're extracting a vector every 10 milliseconds. And so it creates, a huge amount of information that you can feed to your neural network. So yeah, there's a lot I could say about feature extraction, but I'm running out of time. So the next part is how you represent your text. Yeah, so you're feeding audio to your neural net. You're also trying to output text or predict text. And so one thing you could do is try to predict words. But if you're predicting words, you run into a sparsity problem. The model will not learn new words because you're just teaching it, to learn the words that you have in your training data. And so that's a problem because if you've ever shopped on Amazon, there's a new word every, 3 seconds that is invented for product names and so on. And so another thing you could do is character base. So you break everything into characters. But in speech rec, you're learning a language model essentially. And so if the string of text is too long, you may lose context over time. So for example, in here, Hello World has like, 11 characters. You may lose context over time. And so it's better to find something in between that represent words as much as possible. So what you end up going for is called subword units. So basically just like figure out chunks of words that make sense, and you teach your model to learn these subword units instead of words and characters. And I think this method is used in translation and all language modeling also. It's not much different for speech. Okay, and last couple of slides. I just wanted to show the sort of thought process that goes into deciding the architecture of these models. And so I figured I'd start with attention decoding because it's kind of a well-known architecture right now. The power in this is a autoregressive model. So you can see on the right in the decoder with attention, when you output Y1, it goes back as an input to the decoder. So every time you're predicting something, you feed it back to your model. And so it's very powerful sort of predictor model, but it's very costly to run at inference. And so in speech, you know, well, in commercial applications, you care about, you know, speed of your inference. And so what we decided to look into is something called CTC. And CTC is powerful because it's not an autoregression model, so it can output everything at once. But it can only work for certain sequence problems. So it only works when the input and output are monotonic, which means, you know, like it doesn't really work well with translation because some languages, they change the order of certain words. And you require the output to be the same length or shorter than the input sentence, which also is bad for translation because, you know, sometimes if you translate English to French, you'll quickly learn that French is very verbose. And so the output is often very long. But it works really well for speech recognition because we have a really, really long audio. If you recall, like 10 milliseconds, every 10 milliseconds you have a vector. And so you have a really long input and your output is often quite a lot shorter. So I recommend, if you're interested, look up CTC online. There's a lot of good resources. But basically, this solves our problem of speed, but it's less accurate. And so ideally, you do what's called joint CTC attention. So you kind of merge the two architectures together. And so the way you do that is, you know, at the output of the encoder, you put a softmax layer, and then you have your CTC loss and so on top. But you also have the decoder with attention, and you train both in a joint manner. And then actually, this gives you a much better model, but it's just as expensive as the first model I showed you, because now all I did is add another layer of CTC. So instead of using this as a joint model, we use it as a two-pass model. So what we do is we train the whole model as if it was a joint model, and it learns to be a really, really good, accurate model. But at inference time, we use the CTC to create what's called an n-best list. So you have, let's say I said, I love pizza. You might recognize, I love pizza, I love piazza, I love, you know, like, and then you have an n-best list of all the things that your network thinks. And then you use the attention mechanism and the transformer and the decoder attention to rescore that n-best list. And then in that way, you get the best of both worlds. So you get a very accurate system, but also a very fast system. And the cool thing is that it's a very flexible kind of model because you can use it at inference time. You can decide to use it as a rescorer or as a decoder. And so you can kind of decide between speed and accuracy at runtime. But at training time, you're training like the best model you can. So that's sort of the architecture we went for. In the future, Rev plans to recreate these virtuous cycles. You know, so basically, you know, what we did for transcription, ideally we want to do for other languages. You know, with the human feedback, and then eventually maybe translation. Because Rev does transcription, caption, subtitles, and so we can have this human review feedback in translation, and eventually potentially dubbing or other things like summaries and so on. But having the human feedback at every step will really like create this data loop and these amazing models for all sorts of products. And so yeah, if you want to talk about future or the model, stop by at the booth. Happy to talk about it. That's it.
If you have any questions, there are 2 mics. Please feel free to stand up and go there. At the mic, please. They have to get recorded. If you have a question, the mic. All the sessions are recorded on the camera. So, please.
Hello? Can you hear me? Hello? Yeah. So great presentation. I'm just thinking there's a lot of compute power needed to power these models. You have been doing this for some time, so pretty amazing work. How well are you funded, or is it through revenue? Have multiple clients. How are you surviving this? It's a lot of compute that has gone behind this. The first one. The second one is, so you have a transformer architecture to train these things, and they are retraining the models, right? How frequently are you doing it on the errors? Is it like every few hours, every few days? What's the frequency on that?
Yeah. The budget, we can talk offline maybe. We spend a lot of money on it, but the retraining, well, it's a little bit complicated. The model we retrain probably every 3 months or so. But there's a mechanism where we can give some feedback to the model internally. We can do that every week or every day. But we don't retrain the model when we do that. We just like add the information back. We have some special mechanism in the model.
Okay.
Yeah.
Okay.
I could tell you maybe more offline, but
okay.
Yeah.
Awesome.
Yeah.
Thank you.
Yeah.
You can take one more question. Anybody? Any questions you have for yourself?
Yeah. No.
All right, man. Thank you very much.
Okay. Thank you.